It all began at Embry-Riddle Aeronautical University. It was here when I was doing some research on jet engines in the lab, also jet engines on wing, and we developed sensors that were used to try to determine the temperatures and the condition of the most critical components outside the engines. And then I started to expand outside of gas turbines used in aviation and started looking at aeroderivative engines or gas turbines used also in power generation. And I got out of the building, out of the lab, went out and did interviews, got on site to a lot of the power plants to really talk with some of the owner operators to better understand some of the challenges that they were facing. One of the big ones, they were having to operate these engines much differently in the presence of renewables, and they were experiencing more forced outages. That escalated repair costs, operations and maintenance costs, and there was a lot of revenue loss in that process. I really wanted to zero in on this, so I started talking to more operators, talking to other folks, not only who worked on site, but who were also boots on the ground, really trying to understand how did they see their system and their operation. That was really helpful in helping us to then develop our technology that was used to try to solve their problem. We were given an opportunity. Here's our team. We were able to mount our antennas, our sensors inside of these very large engines. And we had to really invent things in real time while we were on site, because what you get in a lab isn't necessarily what you actually see out there in the field. We were able to put our sensors, as you can see here, directly on the blades. These things are spinning like at 3,600 RPM, very large blades. And we routed high temperature antennas inside of the engine's casings. And then while the engine was turned online at base load operation, we were able to, with our computers and electronics, collect the data that our wireless sensors were basically collecting in real time while the engine was in operation. This was a project that we did with Siemens Energy and Duke Energy on 2 units at one of the sites in the Southeast. We learned a lot in that process. We were able to successfully measure blade metal temperatures. But then we also started to expand outside of gas turbine into wind turbines. And we learned that whether it's aerospace or gas turbines used in power generation, also wind operators and owners were experiencing blade problems too. Blades were cracked because of lightning strikes or manufacturing defects. There's some blade root delamination or damage from lightning. We then started to explore this application, and we had to kind of think differently. We used smart cameras where we used the pixels to extract vibration information off of blades, and we were able to show that we can do that using an algorithm that we had commercialized out of one of the national labs. Once we showed that, we wanted to also make sure, like, hey, we weren't making this up. We went to the National Institute of Standards and Technology, NIST, out of Maryland, and we used a laser vibrometer to really calibrate and show that our sensors, our method was very accurate. That led to us collaborating with another national lab, the National Renewable Energy Laboratory. But here on site, we're able to work on a project where we used our computer vision technology to look at things, not just blades, but we expanded to main drive components like gearboxes and main drives. From that, we got the view of the Department of Energy, and we were able to win competitions. And we've also won an opportunity to pilot at the New York Power Authority at Niagara Falls. Here, we benchmarked our system with GE's Bentley Nevada system to show that we were just as accurate, getting the same information as a very expensive system compared to low-cost, off-the-shelf cameras, whether it was a smartphone or security cameras. Here's an example of a smartphone that we were able to get the same quality of data that these $500,000 instrumentation suites would cost, but we were able to just simply capture a video of the shaft while it's rotating here in this hydropower turbine. And I was able to just upload that into our software, and we're able to quickly show what the motion, the amplified motion, the vibration, and what it looks like. And then our algorithm takes it a step further, and it uses a AI blind source separation technique to separate all the different ways in which the shaft can move and rotate. And then we were able to show on other pieces of equipment, on compressors, and being able to show the very subtle vibration. And that led to the door opening up with the NREL's Westgate program, where I became a fellow, where I was invited to continue to better develop our product using national lab resources and subject matter experts in the field. So I'm here in Denver, also in Daytona Beach, and we have a presence in Chicago through the M-Hub Accelerator. You know, it takes a village to raise a kid. It also takes one to raise a company and a technology. And so here's another example on how we were able to take video for one of my colleagues who had a weird noise on one of his circuits, and we just uploaded it in our system. We're able to show the vibration and show where the source of noise was coming from. And we've also expanded our research working with the Advanced Power Electronics and Electric Machines Group, APEM, and NREL. We're doing research on the latest and greatest power modules, inverters, doing reliability studies on electric motors. And so here's an example of a video captured using a simple cell phone. And what we're looking at are the wires that are very prone to reliability issues, like failure because of driving or because of the temperature, the humidity, depending on where these electronics are being used. We're able to show the effects that vibration has on these components and generate heat maps to show where the reliability prone areas exist. That helps researchers get through the iteration process a little faster by better understanding where potential reliability issues are in the first two prototypes and not the 12th or the 15th or 20th prototype. Then there's a lot of rework, a lot of time lost, and a lot more money involved in those cases. We're able to use even infrared cameras. So here's an example of a FLIR video that was captured. And this is not temperature that you're seeing. These are actually the heat deflection map of where the most vibration or displacement was happening. Here, it is an IR video. Here's IR video. Here's the motion being amplified and all the different modes. And here's a heat map that shows the areas that have the highest amount of displacement or mechanical motion for this particular design. What we're able to show with maps like this, we're not saying that this is a failure. What we're saying is this is likely for this design where most of your mechanical motion is happening. And if there were to be an issue, it's likely that it may happen in these areas first. This helps with A/B testing different designs, different cooling mechanisms, different material systems that have less of an impact on vibration or the reliability of the system. Thank you all for allowing me to share my story. For more information, please reach out. Visit us at VIDEOMAGIC.io.